We've been talking about how there are connections between magnetism and electricity. The first one was a charged particle moving in a magnetic field feels a force. Today we're going to be talking about currents causing magnetism. So if I have a wire with a current going through it, it will cause a magnetic field that wraps around the wire. So the current is going to make a magnetic field around the wire. For the direction, we use right-hand rule number 2. Okay, and for this, our thumb is the current, and our fingers wrap around in the direction of the magnetic field. And again, the right-hand rules are a little confusing to you. I've done them a couple times, then they are pretty straightforward. So for this particular example, I have my current going to the right. I'm going to redraw it down here. So I have I going this way. So I can imagine, say, that this pen is my wire. My thumb goes in the direction of the current. So my thumb is going to point this way. Now my fingers are wrapping around the wire like this. So they're coming out above it and going down in below it. If I was to draw it, it might look something like this. Okay, it's going out above the wire, curling down in front, and then around behind it. Another way to draw it is I might just do this, and it's coming out above it and in below it. So out is dots, and in is X's. I usually just end up drawing it like that because that to me is a little bit clearer than this picture here. Now the math for it is that the magnetic field is equal to mu0I over 2 pi r. So the stronger the current, the greater the magnetic field it's going to create. The farther away you get from the wire, the weaker it's going to get. And this mu0 is a constant. It's 4 pi times 10 to the minus 7. Okay, so we have an example here. We want to find the magnetic field at point P. This current is going to cause a magnetic field in space all around it. We want to find out how big that it's going to be. So, first I'm going to find the direction. So I use my right hand rule, make sure I use my right hand. My thumb points in the direction of the current, which is downward. Then on this side, they're pushing into the page, and on this side, they're coming back out of the page. So in on this side, out on that side. So I would draw X's over here, and dots over here. So at point P, on the right side of the wire, they're going to be coming out of the page. Now for the amount, we use this equation, B equals mu0I over 2 pi r. mu0 is the constant, 4 pi times 10 to the minus 7. I is the current, which in this case is 2 amps, divided by 2 pi. And remember, all of our distances need to be in meters. 4 millimeters, milli is 10 to the minus 3rd. So times 4 times 10 to the minus 3rd meters. Now if I do this, the pi's will cancel here, pretty much everything's going to cancel. The 2's will cancel, the 4's will cancel, and I end up with a magnetic field of 1 times 10 to the minus 4th Tesla. And again, we have to have the direction, so on this side where point P is, it's coming out of the page. Okay, we have another example here. The magnitude and direction of the force between the wires. This is a rather difficult problem. I'm going to label these. I'm going to call this one A, and I'm going to call this one B. The thought process to doing this type of problem is this. Okay, the current in A is going to create a magnetic field at B, and then the current in B is going to react to that magnetic field. So the first thing we're going to do is we're going to find the magnetic field at B due to A. Magnetic field at B due to A. So we're just going to look at the current in A causing the magnetic field. So first we'll do the direction. So if I take the current in A, my thumb is going to be pointing down. My fingers come out of the page on this side, and they would wrap around and go into the page on this side. So I'm going to draw dots over here for out of the page. I'm going to draw X's over here for into the page. Then I'm going to use the equation mu 0I over 2 pi r to find the magnetic field over here because of this wire. So mu 0 is 4 pi times 10 to the minus 7. I'm finding because of A, so I'm going to put the current in A, which happens to be 3 amps, divided by 2 pi, and then r is the distance away, which is 4 millimeters. So again, we have 4 times 10 to the minus 3rd. And that is going to give me a magnetic field of 1.5 times 10 to the minus 4 Tesla. And we said on this side, it's going to be coming out of the page. So I was really ignoring this wire. I was just finding the magnetic field over here because of this wire. Now B is going to react to that magnetic field. We have to find the force on B because of that magnetic field. So the equation for that is going to be F equals BIL. I don't have to worry about the sine theta because out of the page is for the magnetic field and up for the current. They're at right angles to each other, so I don't have to worry about the sine of theta. I'm going to plug in my values. The B we just found is 1.5 times 10 to the minus 4. The I over here is 3. And the length of the wire is 0.1 meters. And when I multiply this all out, I'm going to get 4.5 times 10 to the minus 5th newtons for the strength of the force. We also have to find the direction of the force. So for direction of the force, I go back to my first right-hand rule. So my current is going up. If you remember, I had my thumb is the current for that right-hand rule. My fingers are the magnetic field, so I got out of the page over here. So my fingers have to point out of the page, and now my palm is pushing to the right. So the force is going to be to the right on this wire. Now the force on A is going to be the same, but in the other direction, because they're going to be equal and opposite forces.